Quadratic functions. Our objectives are to recognize characteristics of parabolas and understand how the graph of a parabola is related to its quadratic function. Here, let's walk through the features of quadratic graphs. Let's find the items below for the quadratic graph shown. The vertex. The vertex is this point here at the extreme bottom of the parabola. If the parabola is opening down, it would be the highest point. Here, it's the lowest point. So the vertex is the point 3, 1. The axis of symmetry is this line that you can see. You can envision it going down through the middle of that parabola. If you had drawn this on paper, you could fold it on that axis of symmetry and the two sides would touch each other on the paper. So that axis of symmetry is a vertical line. We want to make sure that we have its equation as the equation of a vertical line. So it is x equals 3. Notice it's the x part of the vertex. The maximum or minimum value. It's either going to be a maximum or a minimum. This function has no maximum value. You can see arrows at the ends here. It continues upwards forever, but it does have a minimum value, and that minimum is a value of 1. So we'll circle minimum and say that the minimum is 1. Notice that this 1 is the y part of the vertex. The domain. Remember, the domain is all of the x values that could happen in that function. And we can see, again, this is going this way forever and this way forever. So our domain is coming from negative infinity and going to positive infinity. The range now, we're going to read from bottom to top, and the lowest y value that we see there is 1, and it is included. And then we move up to positive infinity, including going on up there. All right, x-intercepts and y-intercept. In this particular graph, we have none on the x-intercept. So just no x-intercepts, just write none, or it does not exist. It doesn't dip down low enough for us to be able to cross the x-axis on this particular one. The y-intercept, right there, y-intercept is going to be a point 0, 7. Make sure that you write that as a coordinate. And the sign of the lead coefficient a. All right, when we are looking at a quadratic like this, remember it is y equals ax squared plus bx plus c. We take a quadratic, we set it equal to y, and then it's a quadratic function there. So the sign of that lead coefficient is positive. If this a had a negative value, then our parabola would be opening downward. Okay, so you can remember it is positive. If a is positive, it's going to be a happy parabola. And if a is negative, he's going to be a sad parabola. It's positive to be happy, it's negative to be sad. Now, just like there are different forms for a linear equation, there are different forms for quadratic function. So let's start with standard form. A quadratic function in standard form looks like y equals ax squared plus bx plus c. A is the lead coefficient, just like we saw in the last example. C is going to be the y-intercept, and that happens because if we force x to be 0 so that we're staying on the y-axis, then that makes this term go away and this term go away, and y will end up being c. So you can see there that the c is the y part of the y-intercept. And this is an example, y equals 2x squared minus 20x plus 53. Now in vertex form, the quadratic function in vertex form is going to look like y equals a times x minus h quantity squared plus k. And just to be sure, you see this a here? That's the same a that's going to show up there. So a is still the lead coefficient. If we would square that out and go ahead and distribute that a through, a would be the coefficient of x squared. So it'll have the same effect on the behavior, either opening up if it's positive or opening down if it's negative. HK is going to be the vertex. Now we can't just look at this standard form equation and tell what the vertex is, but we definitely can look at the vertex form and see what the vertex is. So whatever number is here is the x part of the vertex. Whatever number is there is the y part of that vertex. Here's an example of your parabola that is in vertex form. In fact, these will be the same parabola. It's just that this one is in standard form and this one is in vertex form. If you wanted to change vertex form to standard form, you would just square this binomial, distribute the 2 through, and then add 3, and then it'd look just like this one that's in standard form. All right, let's go ahead and compare linear and quadratic forms. With a linear equation, we start off with slope-intercept form, y equals mx plus b. With quadratic functions, we call our basic form standard form, y equals ax squared plus bx plus c. Very similar form, set in y equals form, and we don't have any parentheses. Everything is in descending order on that right side. In linear equations, we have point slope form. Now we have changed the way this is written. You're used to seeing it y minus y sub 1 equals m times x minus x sub 1. And in this form, we've made it as a function by adding y sub 1 to both sides and getting this form. That's your point slope form. And when we look at that form, we can tell where we have shifted the line. Okay, we've shifted it x1, y1. Okay, and when we're looking at vertex form, we can see what that shift is. We've shifted it h and k. Standard form for a linear equation is going to be ax plus by equals c. And we found that was a nice form when we were working with linear equations to be able to get your x and y intercepts. And that's really about it. You can't get too much more out of that. Now we do need to mention that standard form for a linear function is not analogous to standard form for a quadratic. You can see the forms are quite different even though they both use the word standard. Now the letter that stands for the y-intercept also is going to differ. When we looked at slope-intercept form here, you had a y-intercept of 0b. And when we look at standard form over here, it's 0c. Now, graphing a quadratic function. Let's look at graphing the quadratic y equals negative of x minus 2 quantity squared plus 3 and find the items below. Now this equation is in vertex form. Remember, that's y equals a times x minus h quantity squared plus k, and the vertex is given by hk. When we're looking at this, it's x minus the h. X minus the h. So my h is 2, and plus k is just the number that is tacked onto the end. That's a positive 3. Your axis of symmetry, remember, is going to be the x part of the vertex. So x equals the x part of the vertex is your axis of symmetry. Your domain is going to be all real numbers, negative infinity to positive infinity. We saw that in a previous graph, but if you're looking at this function here, there is nothing mathematically that's going to keep you from subtracting 2 from a number, squaring that number, multiplying it by a negative, and adding 3. We can do that to any real number. So the domain is all real numbers. Let's get the vertex on there, the point 2, 3. Here's your axis of symmetry. Okay. I'm noticing this. A is negative. So this is going to be a parabola that's opening down somehow. Okay. So I do know that my range is going to be coming from the bottom up. It's coming from negative infinity, and it goes until 3 and includes 3, but then it stops. Okay. Well, we need to go ahead and get some other points in there. One thing I like to do is just do a quick t-table, and the vertex you'll want to put kind of in the middle. You kind of think of it as your center or your folding point of that parabola. If you can stay close to the vertex with your other x values, then you're going to get some graphable points. They won't get too large for you to be able to graph on the grid you have. So let's go ahead and go 1, 2 away this way, 1 and 2 away this way. Go ahead and put those in. Let's start with 0. 0 minus 2 is negative 2. Negative 2 squared is positive 4. Positive 4, we're taking the opposite of that, so that's negative 4 plus 3. That's going to be a negative 1. Let's try with 1 now. 1 minus 2 is negative 1. Negative 1 squared is positive 1. Then we're taking the opposite of positive 1, which makes that negative 1. And negative 1 plus 3 is 2. Now 3. 3 minus 2 is 1. 1 squared is 1. The opposite of 1 is negative 1 plus 3 is 2. Seems familiar. 4 minus 2 is 2. 2 squared is 4. The opposite of 4 is negative 4. Negative 4 plus 3 is negative 1. Notice the symmetry in the table, and it's all around that vertex. Okay, so we've got some other points we can graph. We have 0, negative 1. We have 1, 2. We have the 2, 3 as our vertex, 3, 2, and 4, negative 1. Now, they did not ask for the x-intercepts, or we would find them. Okay. Just try and make it as smooth as you can, graphing that. Nice smooth sides. They did ask here where the graph is increasing and where it's decreasing. I can see that I am increasing from here to here. So how do we express that in terms of x? Remember, these intervals need to be described in terms of x. All right, so we are going to start from the left, and we see the arrow is going that direction forever. So we're coming from negative infinity, and we go until an x value of 2 here, an x value of 2, before it stops increasing. Okay, and then that x value at 2 and on to infinity, our graph is then decreasing. So a question we pose here is, why is 2, 3 the vertex of y equals negative of x minus 2 quantity squared plus 3? And the answer is transformations. Remember, when we're looking at just a regular parabola, y equals x squared, we've got a transformation going on when we talk about shifting to the right 2. We have x minus 2, and that shifts it to the right 2. And then 3, remember the vertex used to be at 0, 0. Now it's at 2, 3. So we've shifted it right 2, and now we need to shift it up 3. So it would be a y minus 3. And then we also have the fact that this parabola was opening down. That's another transformation that has no bearing on the vertex in this instance. So we have this, but we always like to have it solved for y. So we're going to add the 3 to both sides and get it in this form. And so that's the reason that vertex form works the way that it does. All right, when we look at the form f of x equals ax squared plus bx plus c, the vertex is still a very important point. We still have to be able to find it. And we have this formula. The x part of the vertex is going to be negative b over 2a for the h, and f of negative b over 2a for the k. In other words, we'll find negative b over 2a, and then we plug that into the function to see what k goes with that h. So let's go ahead and graph this and find the items below, not necessarily in that order. We want to try and find the vertex first. Let's see, I have negative b over 2a is going to be my h. That is the opposite of b. The opposite of negative 6 is positive 6. Divided by 2 times a. 2 times 3. So I have 6 divided by 6, which is 1. So I know that the h of my vertex, the x part of the vertex, is 1. And now I can go ahead and put the 1 into the function and get the y out. So I'm going to have y equals 3 times 1 squared minus 6 times 1 plus 2. So 1 squared is 1 times 3 is 3 minus 6 times 1, which is negative 6, plus 2. 3 minus 6 is negative 3, plus 2 is negative 1. So my vertex is 1, negative 1. I can go ahead and graph that. The axis of symmetry is the vertical line, x equals the x part of the vertex. And I know the domain is going to be all real numbers. the range, let's figure that out after we've got a little bit more graphed. Let's make a t-table here. So I've got x and y. And remember, we'll keep the vertex in the middle of that t-table. 1 and -1. Let's go a couple this way and a couple more this way and plug those in. If x is 0, I'm going to have 2. If x is -1, this would be -1 squared is 1 times 3 is 3 minus 6 times -1 makes a -6, so that makes +6 plus 2, so that's going to be 11. Okay, and let's try a 2. 2 squared is 4. 3 times 4 is 12 minus 6 times 2 is 12 plus 2. And it looks like that's right. We've got symmetry around that vertex. And for 3, we should be getting 11. Let's make sure. 3 squared is 9 times 3 is 27 minus 6 times 3, which is 18, plus 2. This is going to be a 9 plus 2, which is 11. So definitely we've got our symmetry working for us. Kind of a way to double check as you're doing your problem. I've already have my, my vertex graphed. Let's go ahead and graph 0, 2. Let's graph 2, 2. And once we get much further away from that, because we're stretching this so much vertically, we're going to go way off of our grid, but we do know that at least it's going to grow really fast because it's going to get up to 11 by the time we get over one more unit on the x. So it looks like our range is starting at -1 inclusive and going to positive infinity. We're increasing from 1 to positive infinity, and we're decreasing from -infinity to 1. Remember, these are described in terms of x, and remember that these are open intervals. We do not include the endpoints on those. Now let's find the equation for this quadratic graph. If we have a nice graph with enough information, we can identify the vertex in some other point, then we should be able to get everything that we need to get the equation for that graph. I'm looking at the vertex. It looks like our vertex is 2, 1. And we can use that and use the vertex form. Remember, vertex form is y equals a times x minus h quantity squared plus k. But I know my h is 2, and I know my k is 1. Now this is great, except that we don't know what a is. So I'm going to need to solve for that. Let's go ahead and identify another point. Now you want to identify a nice point that's going through some crosshairs, like this one, this point 3, -1. Okay, now this is just an x, y point that happens to be on that quadratic graph. So let's go ahead and substitute that point in, and then the only thing we'll have to find is a. So my y is -1 equals the a that I'm trying to find times my x, which is 3, minus 2 quantity squared plus 1. And now this is easy enough. We can go ahead and simplify. 3 minus 2 is 1, and 1 squared is 1, times a is just a, plus 1. Then I subtract 1 from both sides, and I get a is negative 2. So I can come back up here to my vertex form and now replace that a with the value of a that I found of negative 2. So y is negative 2 times x minus 2 quantity squared plus 1. You'll notice here a is negative, and indeed our graph is opening downward. So you don't have to worry about if a is positive or negative in this process. If it is positive, it will come out to be positive when you're solving over here. And if it's negative, that negative will show up when it's supposed to. Now let's say that we're trying to find an equation from intercepts. We don't have a graph, but they've listed the intercepts for us. We have two x-intercepts of negative 2, 0, and 3, 0, and the y-intercept of 0, 7. So we can find the factors from those x-intercepts. Well, we know that if we have an x-intercept of negative 2, 0, it must have come from this factor of x plus 2. If we have the x-intercept of 3, 0, that must have come from the factor of x minus 3. So let's go ahead and set up this factored form and FOIL it. Here's our factored form. Foiling it, we get x squared minus x minus 6. Okay, so now I have this y equals sum a, y equals sum a times all of that. Now I need to use another point to solve for a. Well, 0, 7 is a y-intercept, but it's perfectly fine to use it as your other point. So we'll go ahead and do that here. Y is 7 equals a times my x is 0 squared minus 0 minus 6. Well, when I simplify everything in those parentheses, I just have a negative 6. And multiplying that times a, I have negative 6a. That equals 7. Dividing both sides by my negative 6, I get a equals negative 7 6. So let's go ahead and plug in that a value and distribute. We had y equals my a, which I now know is a negative 7 6, and I have x squared minus x minus 6. So this ends up being y equals negative 7 6 x squared plus 7 6 x plus 7 plus 7. So let's look at an application of quadratic functions. Here, the concentration of medicine in a certain patient's blood is modeled by C of t equals negative 1.528 t squared plus 10.023 t, where t is the time in minutes since injection and c is in milligrams per liter. Let's find the following. The concentration after 1 minute. Well, 1 minute is going to be your time t. So we're going to take c of 1. That's negative 1.528 times 1 squared plus 10.023 times 1. So a negative 1.528 plus 10.023, and that gives us 8.495. So we've answered it numerically, but we need to answer it as a word problem. They asked the question in words. We need to answer in words. So after 1 minute, the concentration is 8.495, and the unit there is going to be milligrams per liter. Now in part 2, they want the maximum concentration and its time, the time that it takes to get to that maximum concentration. At first it seems like you don't have enough to be able to answer this. In part 1, at least they gave us the time. Now they're asking for the time and the concentration. But we need to focus in on one key word here, and that's the word maximum. In fact, if you notice in your quadratic function, we have a negative a, which means this is an upside down parabola, and the maximum concentration is going to be where that vertex is. Okay, so I'm looking at h being negative b over 2a. So negative b would be negative 10.023 over 2 times a. A is negative 1.528. So that would give me a negative 10.023 on top and a negative 3.056 on the bottom. When I perform that division, I'm going to get, we'll say, approximately 3.2798. All right, and that's going to be your t. It's the x part of your vertex. Here we're talking about t, time, so this is going to be in minutes. Okay. You might even round that to 3.3 minutes. Just depends on what your homework is asking you to do. And then we need to find k. So we're taking c of that 3.2798. That's going to be a negative 1.528 times 3.2798 squared plus 10.023 times 3.2798. And putting this into the calculator, I'm getting a negative 16.404, just approximately, and plus 32.873. And when I combine that, I'm going to have approximately 16.469. And that's going to be the concentration, which is milligrams per liter. So the maximum concentration is 16.469 milligrams per liter. Maximum concentration. And 3.2798, or you could round it to 3.3 minutes, is the time at the max concentration. Now we've already learned about quadratic inequalities, but I'd like us to be able to connect what we've learned with graphing quadratics to quadratic inequalities, or our nonlinear inequalities. So let's solve this quadratic inequality graphically. I'm going to go ahead and distribute my x through that. We want to go ahead and get it into the form that we had before. X squared minus 5x plus 6, where it's all on one side with the 0 on the other side. Okay, so now I'm going to say, let's go ahead and get this graphed. Let's say if this was an equation, y equals x squared minus 5x plus 6. My vertex is going to be negative b over 2a for the h part of the vertex. That's going to be a positive 5 over 2 times 1. So the vertex has a x of 5 halves. And then plug that in to the function, and we'll go ahead and get the y part of the vertex, the k. And so I'm going to have 5 halves squared is 25 fourths minus 25 halves plus 6, and that is a negative 1/4. So my vertex is at 5 halves, negative 1/4. Let's go ahead and graph that. That'd be 2.5 and a negative 1/4, so about right here. And this parabola is opening up. Let's see where we can find the x-intercepts. If we had to factor this like we did with quadratic inequalities before, we factored it as x minus 2, x minus 3, and that was less than equal to 0. So here I have a 2 and 3 on the x-axis as my x-intercepts. And this is a rough sketch of that graph. And when we're graphing this, we see part of the parabola is above the x-axis and part of it is below the x-axis. So what is the part that we want? It says here the parabola that we've graphed is less than or equal to 0. And for us, that means we're going to want this piece, the part that's between 2 and 3. And that's our solution. 2 to 3, including those endpoints, is the place where the graph is going to be below 0, below the x-axis, or right at the x-axis.